Hi chemistry students, this is Mrs. Miller, and today we're going to be talking about phase changes. So we're going to be talking about this whole diagram that you guys see off to the right hand side, and we're also going to be talking about what it means to be endo and exothermic, and then finally we'll just wrap up with a heating curve for water. So you guys are going to want your note sheets out, so you can be filling out a few diagrams with me and filling out some notes for endo and exothermic. You guys should all have this phase change diagram somewhere in front of you. If you don't, I would highly suggest you guys write this on a sheet of paper, but you are going to see it on that note sheet that we gave to you guys. So when we start going through phase changes, we're going to be looking at two different types of phase changes, and that would be exothermic, which I'm going to write in red, and then there's going to be endothermic, which I'm going to write in blue. So we're going to start with the ones that you guys already know. And the first one we're going to go with is where we turn from a solid into a liquid. And this, of course, is called melting. Okay, so melting is going to be an endothermic process. So on the opposite end of that is where we go back from a liquid into a solid, and this is what we call freezing. And freezing is going to be exothermic, or energy is going to come out, versus melting, energy is going to go in. So another common one that you guys already know of is where we go from a liquid up to a gas, and when we do that, that is what we call evaporation. And because I'm drawing that one in blue, of course, that is going to be endothermic. The opposite side of that is where we go from a gas back down into a liquid, and this, of course, is going to be condensation. Okay, a little messy, but you can tell that's condensation. And of course, that one is going to be exothermic, or energy is going to come out. The last two are two that you guys might not know because we don't see them super often. So one is where we go directly from a solid into a gas, and this is going to be called sublimation. And that is going to be endothermic. Good example of sublimation is where we have dry ice. It's going directly from a solid, and we're seeing it almost looks like gas coming off of it. So some people use it around Halloween to look like a witch's brew. So that is where we're going to see sublimation. The opposite side of that is on some occasions we can have a gas that goes directly into a solid, and this is what we call deposition. And this one is going to be exothermic because it's going to have energy come out of it. So when we look at this completed phase change diagram, we can see that all of our endothermic ones are where energy is going to go into that object. Those are going to be in blue, and in this case on the inside. And when they're exothermic, they're going to be on the outside, and they're going to be in red. Next, we'll talk about what it means to be endo and exothermic. First, we're going to be talking about endothermic reactions. So endo means inside reaction. So what's happening with this endothermic reaction is where there's going to be a change in matter in which the energy is going to be absorbed. Okay, so energy is going into this system. So I like this picture a lot where we have this beaker with these little squiggly lines coming in. Those little squiggly lines would be energy coming in. So energy is coming into this blue liquid. Energy is being absorbed from the surroundings or from the outside, and as a result, the temperature of the surroundings or everything on the outside is going to get lower. It's going to drop. So a good example of this would be like a chemical cold pack, or those cold packs that they keep in first aid kits where you have to kind of break them and things like that, and as soon as you break them they start to feel cold. So that's an example of an endothermic reaction. And again, endothermic reactions are where we have energy being absorbed, and because the energy is being absorbed, these reactions have a tendency to feel cold because energy is going to the inside and it's leaving that outside feeling cold. The opposite of the endothermic reaction is the exo or outside reaction, exothermic reactions. So exothermic, we look at it, therm means we're talking about heat, and exo, so heat outside. So what we see with exothermic reactions is any change in matter in which energy is now released is going to be an exothermic process. Good examples that you guys tend to like are burning things or explosions, because both times if you burn something or you have an explosion, you're going to see a good exothermic reaction. And the way that you know that it's an exothermic reaction, not only does this process release that energy, but the big one is it tends to feel warm to the touch. So sitting outside in the middle of summer and there's a bonfire, you can feel that warmth coming. So that's a good example of an exothermic reaction. Another good one would be like hot hands, where you have to take that little pouch and you rub it, and as you rub those pieces on the inside all together, they start to warm up for a long period of time, so that heat is coming out from that reaction. So then as an overview, I want to take all of our phase changes that we talked about and link them to either being endothermic or exothermic. So in that picture that you guys created, I wrote them in two different colors. So blue meant endothermic, because blue I always think cold, and then I wrote the exothermic in red. On here I have them as orange just because the text looks weird if I do it in red. So endothermic absorbs energy. Remember, endo, inside, thermic, heat, so heat goes inside, so it's going to feel cold. The three that we're looking at might seem a little bit weird, and that would be melting, evaporating, and sublimation. We know that melting is where we go from a solid to a liquid, evaporation, liquid to a gas, and sublimation, solid to a gas. So think about those particles. In order for these particles to go from one of these phases to another phase, they have to absorb energy so that those particles move faster. So here we have a solid, which our particles just barely vibrate back and forth, to the liquid, where those particles are able to move faster and they move past one another. So in order to do that, they have to absorb that energy, move faster, and now we're in a liquid state. So that would be the same of all three of those. On the opposite side of that, we have that exothermic reaction. Exo, outside, thermic, heat. So heat goes outside. So they're going to feel warm. And it seems weird that freezing, you're going to start to feel warm. Odd, but true. Condensation and deposition are also true of these. So when we look, we have a liquid going to a solid, gas to a liquid, and gas to a solid. So let's look at freezing specifically. Why is that exothermic? Why does this make sense? Again, we have our liquid, which our particles are moving a little bit faster, and they're able to move past one another. And then they have to turn to a solid. So they need to really slow down. The only way for them to slow down is to have that energy leave and go to the outside, and then as they lose that energy, they slow down and become a solid. So while we think about freezing, that it gets colder, it's getting colder because the heat is moving out. The last thing I want to go through with you guys is a heating curve for water, and we're going to consider this to all be at normal or standard pressure, which is going to be 1 atmosphere. So if you notice, up on the y-axis we have temperature in degrees Celsius, and then on the x we have heat added. So you can see our line is going to go up, it flattens, up, flatten, and up again, and then we have 3 bubbles that we want to be able to fill in. So when we start here, we can see that we are going to, as we increase the heat, we're also going to be increasing the temperature a little bit here. So when we have low temperatures, you guys probably already know this, but we have low temperatures, which is a direct correlation to the amount of particle movement. So right away, I know that that's going to be low particle movement, so this is going to be a solid. As I keep going, so the solid in this case would be this part of the line. Okay, so it's a solid until all of a sudden it reaches a point where it's going to do something. And at a certain temperature, as you guys can see on here, it starts to flatten out. And the temperature for water that actually happens at is going to be 0 degrees Celsius. So let me get that written on here. We have, oops, that's a little high. I can't quite get all the way over to that part of my graph, but that's going to be 0 degrees Celsius. Okay, so at 0 degrees Celsius, what all of a sudden is going to be hit is something called the melting point. So as you can see, at this point, when we're looking at it, the temperature is staying exactly the same as we go across this, but heat is being added. So what's happening is the temperature stays the same while the substance melts until all of that substance turns into the next phase. And of course, the next phase that we're going to see is going to be a liquid. So liquid on here is going to be this part of the line. All right, so we're going to continue to add heat, and as we continue to add heat, we're going to see that this liquid eventually reaches another flat spot. And this time, this flat spot is going to be the boiling point. Wow, that looks really bad, but you guys can figure it out. Okay, my stylus is kind of breaking down on me. So we have the boiling point where you can again see that the temperature levels off even though heat is being added, and we're going to stay at this temperature until all this liquid turns into the next phase. So the boiling point for water is going to again occur at a very specific temperature, and what we see, I'm going to write my line up here. Again, I can't make it go where I want it to because I have this little thing on my screen, but this will be 100 degrees Celsius. So between 0 and 100 degrees Celsius, we're at a liquid. Below that, we're at a solid. And then when we go above that, we, of course, have reached into the gas phase. So the gas phase will be this part on there. And we can see that anytime we get to a temperature for water that's over 100 degrees Celsius, we're going to be in the gas phase. That's after we reach that boiling point. So again, low temperatures, we're going to start with a solid, low particle motion. We're going to stay that way until we hit 0 degrees Celsius. That's when we hit a melting point, and that's when we're going to start moving into the liquid, hitting the boiling point, and going into a